Hello class, today we are going to go over lesson 5.5, solving rational inequalities. Notice that I've highlighted the term inequalities here because this should ring some bells back to solving polynomial inequalities back in Unit 4. So remember we solved those graphically and algebraically, and when we solved polynomial inequalities algebraically, we always had to use an interval chart. So it's going to be very similar that way today as well. But before we go into algebraically, we will do graphically first. So let's just remind ourselves that if I asked you to solve a rational equation, which was the lesson prior to this, it typically consists of one answer, okay? Or it could just be, for example, x equals 3, x equals 4, right? Whereas the solution to a rational inequality consists of a range of answers, and that's because the inequality symbol will leave you with something like x less than 7, x greater than 4, or x is between -2 and 3. So there's always a range or an interval that represents the answer to an inequality. So that will be the same today. Alright, so what are our steps for solving an inequality graphically? When we do rational inequalities, you're going to notice a lot of the steps are the same as when we solve polynomial inequalities graphically, except there's one key difference. So our first step, remember, was to always graph the functions on either side of the inequality on the same grid. Then what we did is we always tried to look for their point of intersection. We are still going to do that today. Okay, so we still look at the point of intersection. However, we also have to consider the vertical asymptotes. Okay, we never had to do this before because we knew polynomial equations didn't have vertical asymptotes. So now that we're dealing with rational, we have to think, okay, the x-axis gets cut up according to the point of intersection, and then obviously where vertical asymptotes occur because the graph is undefined at that point. If I ask you to solve where f of x is greater than g of x, then all you're doing is looking where the graph of f of x lies above the graph of g. Okay, so in other words, when does f have larger y values? And then obviously vice versa. If I ask you to solve where f of x is less than g of x, you're looking where the graph of f lies below the graph of g, or wherever it has smaller y values. All right, so let's try this question here. Before we get into solving inequalities here, what I want you to get used to doing is seeing how the x-axis gets divided up according to the intervals. So remember here, the intervals are going to be created by the x values you get from vertical asymptotes and from the points of intersection. Okay, so coming down here, I want you to look at these two graphs. Okay. As you start from negative infinity, so let's track across from negative infinity, I want you to stop at the x value where a point of intersection occurs or where a VA occurs. So as we go along, oh, okay, this is an x value in which there is a point of intersection. Okay, and that occurs at -3. Okay. So I know that's my first key value. So I just kind of drew a little number line at the bottom here so it doesn't look so busy up on the graph. All right, so that x of -3 is a key feature. All right, as we leave -3, we keep traveling along, and then look what happens. We hit a vertical asymptote next, and that happens at -2. All right, keep traveling along the x, and then a vertical asymptote. Another one happens at 2. And we keep traveling along, and then we don't see another point of intersection, and those two won't cross again. So what we have done here is with these three key points, remember always x values, okay, so I always want you to think of this as x values here. We have divided it up into 4 intervals. So we have to deal with all x values less than -3, so that's interval 1, Interval 2 is between -3 and -2. Interval 3 is between -2 and 2. And interval 4 is greater than 2. Okay, so that is the first thing you want to do for yourself with any question, because a lot of times students will incorrectly identify the intervals and therefore will not answer parts B and C correctly because they missed one of the intervals. Okay, so if I wrote all those intervals out in interval notation, it would be -infinity to -3, -3 to -2, -2 to 2, and 2 to infinity. All right, so next up, and this is where a highlighter might help. So if I wanted to answer where is f of x greater than g of x, that means I want to know, in my graph here, f of x is blue, when does the blue graph lie above the red graph? So with your highlighter, okay, I want you to highlight where you see that. So where is blue above red? So right here I notice it. Right? So blue is above red in this section here. Okay, so that's going to be one interval, so interval number 1. All right, between these two, nope. Between these two, yep, I can see that the blue graph lies above the red. And then in this interval, no, the red is above the blue. Okay, so now we're going to write out. So that means the solution to this inequality will be intervals 1 and 3. Okay, so we're going to say, therefore, the solution is that x is an element of -infinity to -3 in union with -2 to 2. All right, now it's asking for when f of x is less than g of x. So we'll use a light blue highlighter here. So again, now I'm asking you, where is the blue graph below the red? Okay, so that should be for the other intervals left over, but just in case I gave you this question first, I want to make sure you understand where it comes from. So obviously not in this interval here. In this interval here, if you look very closely, I know it's hard to see, but between -3 and 2, you can see that the blue graph lies underneath the red one up here. So that's one interval. Not in this one. And then in this section here, I can see that the blue graph lies below the red. So the answers for this one, so that's going to be 2 and 4. Whereas 1 and 3 applied to the other inequality. So that means the solution to f of x is less than g of x are the intervals -3 to -2, so this section here, in union with 2 to infinity, so right here. All right, so now let's try some more of these. So notice that I give you the full equations here. I did not identify on the graph which side of the graph represented what graph, so that just has to come from your knowledge. So for example here, I decided to draw it over in colors because I find that is a bit helpful for students. So if you guys want to do the same thing, the original graphs were just in black and white. So what I did is I called this function on the left side of the inequality, x minus 7 or x plus 2. I know that that's a rational function. I'm just going to call it f of x for some organization. So I know that's a rational function. What are some things I know about it? I know that it has a vertical asymptote at -2. And I know that it has a horizontal asymptote at y equals a over c, so 1 over 1, so just 1. Okay. And that's because from last lessons, the degree of the numerator is equal to that of the denominator. So that's why we knew this was going to be the case. So the reason why I did this is not only to verify that when I draw over this in red marker, I'm drawing over the correct red graph, but it's also important because the graph didn't clearly identify asymptotes. So notice I want everyone to draw in the vertical asymptote for x equals -2. and for y equals 1, because those were very hard to see just from the graph. All right, the function on the right side was 3, so we know if that was g of x equals 3, that would be a horizontal line through 3. Okay, so you can draw that blue line there. All right, remember I told you the next step that you should do is that you should identify your key x values and then come up with your few intervals. So the first thing, remember, you want to look for x values where there's a point of intersection, and you want to look for x values where there's a vertical asymptote. Okay, so again, I have that kind of set up at the bottom here. Okay, so we get our first point of intersection occurring right here. So notice I'm just doing a little green dot. Okay, so again, I'm just working with the x-axis. As we keep traveling along, I get my next key point at a vertical asymptote. Okay, so that's my next point that I've drawn here at the bottom. Okay. And as you keep traveling along, you're going to notice that we don't come across any other VAs, and we definitely won't get any other points of intersection because this one is restricted by the horizontal asymptote. So in this graph here, we just had 2 key points. Okay, so if we had 2 key points, that means we created 3 intervals. So now we need to ask ourselves, okay, let's put that down for now. Let's highlight first. Now we need to ask ourselves what the question was referring to. So it's asking, when is f of x, the red graph, when is the red graph above the blue graph? So when is red above blue? All right, so let's take a look here. In this interval here, from negative infinity to, I think that's about negative 6.5. Okay, definitely not here. Okay, red is below. In this section here, from negative 6.5 to negative 2, okay, is the red graph above the blue? Yes, it is. All right, next section, from negative 2 to infinity, the red graph is below. So that's it. So that means that there is actually only one interval that represents the solution here. So there's only one set range of values. And that is, highlight here, interval number 2, okay, which is from negative 6.5 to negative 2. And that is the only solution here. Okay. So negative 6.5 to negative 2. Notice that I use circle brackets because my inequality symbol up here did not have an equal to symbol. If it had an equal to symbol, then I would only put the square bracket with the negative 6.5 because that was a point of intersection point. I would not put it with the negative 2 because the negative 2 is an asymptote and therefore the graph is not equal to it there. Again, you can write in interval notation or set notation. All right, let's try another one. So I'm going to refer to f of x as just the line y equals x. So remember that just means that this is a slope of 1 over 1 and a y-intercept of 0. Okay. So that's drawn here. I drew that in red. All right, on the right, we've got a rational function, 3 over x minus 2. So again, just for practice, what are some things we know about this? Based on the denominator, we know that there's a vertical asymptote at x equals 2. And because the degree of the numerator is less than the degree of the denominator, that means we have a horizontal asymptote at y equals 0. So again, I'm writing that out because I'm going to draw those key features in because they were not given in the actual question. All right, so again, our next step is to create our intervals. So start walking along the axis here, and then stop at an x value where a point of intersection or a VA occurs. Okay, so right here I see a point of intersection occurs, okay, right there at -1. Okay, so that's a key point. I keep walking, walking, walking. Okay, remember you're looking for where the red crosses with the two L brackets because the other two dotted lines are asymptotes. Okay, so they're not where the graph exists. Walking, walking, walking. This point here is a vertical asymptote, so that's one of the key features. Okay, right? We care about vertical asymptotes. Don't worry about this horizontal one. You're going to walk a little bit more, and you're going to stop at 3 because 3 is where there's another point of intersection. So, right, so we're looking at our POIs here and here, and that produces this X value. Okay, and this one produces that one. All right, so that gives us 3 points here. We keep walking, and then they're never going to intersect again, and there's no other VAs. So that means we should have divided our x-axis up like this. Okay. So we have interval number 1, interval number 2, interval number 3, very small in between these two, and interval number 4. So now we need to ask ourselves, get out your highlighters, where is, and remember read it properly here, where is the red graph below the blue graph? Where is the red below the blue? So let's look at our first interval. I can definitely see red is below blue here, so that's one. In this interval here, red is above the blue, so not there. In this little interval between 2 and 3, I can see that the red here is below the blue, so that little section there works. And then from 3 to infinity, I can see that red is above blue, so that's not what I'm looking for. So that means intervals 1 and 2 will be our answers. So we say the solution is from negative infinity to -1 in union with 2 to 3. All right, hopefully everyone was okay with solving those graphically. Okay, so always follow those steps, get out colors if you need to, create your intervals based on VAs and based on points of intersection, and then just identify which solutions apply based on the question given. All right, now we're going to move on to solving algebraically. Okay, so the first step here in solving algebraically is to rearrange the inequality so that one side is equal to 0. Okay, so you can bring all terms to one side right away. What's going to happen then is that you most likely will have a bunch of different denominators for all the different terms that you brought over to the one side. You always want to combine the expression so that it's one term. Okay, so when you have a bunch of fractions and you want to make them all one term, what do we have to do? We can only add or subtract them if they have a common denominator. So we have to rewrite them all so that they all have the same LCD. Okay, that way we can just combine them as one term. All right, so when I say combine it as one term, that means I want it to look something like this. Just writing some stuff at the top. Okay, so I want you to write what I have here in green. So that means I want you to write it so that it eventually looks something like ax plus b all over cx plus d, and then, for example, this is just an example here, is less than or equal to 0. So you bring the terms over, you combine them so they look like one term, and then you have the 0 on the other side. Now, if we got to this situation in the last lesson, so remember, this is a rational inequality, this is a rational equation. If we came to this point in the last lesson, you were able to solve this by cross-multiplying. Right? And what would happen there is then you would just be left with ax plus b equals 0. So were we able to cross multiply there? Yes. And then it would lead to this. What I want you to keep in mind is that you cannot do that with rational inequalities. And what is the reason? The reason is because of that word right there, inequalities. Okay? So, what happens if I were to multiply both sides? So over here, if I were to take this and cross multiply, what would happen is that this cx plus d would be multiplied by 0. But our problem is this. We cannot cross multiply since we do not know if this unknown x term is positive or negative. Since we don't know what x is, if it did produce a negative answer, then when we multiply by a negative, the inequality sign should flip. So if we don't know what x is yet, then we cannot assume that it's positive. We also cannot just cross multiply and cancel out because that would flip the sign and then change the answer. So because we don't know about this and because of that inequality rule about flipping the sign when multiplying or dividing by a negative number, we cannot cancel anything out. And that's the main thing here. So if you highlight that for yourself as much as you can, okay? So unlike with solving rational equations, we were able to multiply all terms by the lowest common multiple and then cancel out denominators that were common. We cannot do that with inequalities. And like I said, that is because we do not know if x is positive or negative, and therefore we do not know if the inequality sign should flip or not. So that's why you have to be safe. You have to leave everything as is, and then unfortunately we do have to keep the denominators when dealing with inequalities. Okay? So just with inequalities, if you have an equation, you are allowed to cancel terms out. Okay. All right, our next step. Once you have it all looking like this up here, you're going to state your restrictions. Okay? And remember, that's wherever the denominator equals 0. This will also tell you where your vertical asymptotes will be. Okay? The next thing you want to find, so you want to find where your vertical asymptotes would be. That's one key feature. The next one is you want to determine your x-intercepts. Okay? So you find the x-intercepts, remember, by setting each factor in the numerator equal to 0. Okay, so those are two things you need to do. Find your VAs and find your x-intercepts. Okay. And then your final step is everyone's favorite, and that is to create an interval chart. Okay. All right, notice here when you create your interval chart, okay, so remember when we did polynomial inequalities, our interval charts only dealt with the roots or the x-intercepts. So we're used to just dealing with this, x-intercepts. But now because we're dealing with rational inequalities, we also have to consider the x-intercepts and the vertical asymptotes because those will be x values where the graph is undefined. Okay? So highlight this, whatever you need to do to remember that with rational inequalities, you have to have VAs and x-intercepts in your interval chart. Okay? And then the rest is all the same that we've been doing. All right, so let's give it a shot. So solve these inequalities algebraically. All right, so the first thing you can do, you can find a lowest common denominator right away and change everything. I personally like to bring all terms over to one side, and set one side equal to 0. It does not matter which side you bring it over to, you will get the same answer either way. So for example, this time I decided to bring the x minus 2 over. Okay. So I brought the x minus 2 over, so I have 0 is less than 8 over x minus x plus 2. Okay. All right, your next step is that you want to rewrite this whole section. You want to rewrite this whole side as one term. We don't like how it's all split up right now, the addition and subtraction of a bunch of terms. So because we've got a denominator here with x, I'm going to pretend the other terms have denominators of 1. Just imaginary ones there. So now you need to tell me what is the lowest common denominator of x, 1, and 1. So the lowest common denominator is x. So remember, we're not multiplying by the LCM here and canceling out because we can't cancel things out. But what we can do is we can rewrite these two terms in another format. Okay? So if I need to get this bottom to equal x, I multiply the bottom by x, and whatever I do to the bottom, I do to the top. The same applies to this term. I need to get 1 times x, and therefore I also have to do 2 times x. That leaves us with this. So 8 over x minus, and then that's going to be x times x over x, plus 2 times x over x. What does that equal? Notice that because they all have the same denominator, now I can bring all these terms together, okay, as the numerator. All right, so I have 0 is less than 8 minus x squared, x times x, and then plus 2x, all over x. All right, I'm just going to rewrite that here. Okay. So notice that I rearranged it so it looked like nice in nice descending order. So it looks like a nice trinomial. So we have negative x squared. So that's a negative there. You just can't see with the circle there. Negative x squared plus 2x plus 8. So I just rearranged it to look nicer. Okay. Now, before we move on, it will always be helpful for us to make sure that the numerator and denominator are in factored form. Okay? And you're going to see why. So let's always put in factored form if we can. So that means I'm going to look for, or how to factor negative x squared plus 2x plus 8. So the first thing to do is going to be to factor out a GCF of negative 1. Okay, so I brought negative 1 out, and I'm left with x squared minus 2x minus 8 all over x. All right, so at the side here now, I am trying to factor this simple trinomial. So I'm looking for two numbers that multiply to negative 8 and add to negative 2, so that's negative 4 and 2. So this should be my final line. 0 is less than negative 1 bracket, x minus 4 bracket, x plus 2 bracket all over x. All right, so this is the final answer we want. And the reason I wanted you guys to put it into the numerator into factored form is because, remember, before we do our interval chart, we need to know what the x-intercepts are. And we know what the x-intercepts of rational functions are wherever the numerator equals 0. So if I want to know where the numerator equals 0, that would have been really hard to find just from the purple form, because later on I would have had to factor anyway. So at the side here, okay, we should be asking ourselves a few things. One, what is the vertical asymptote? Our vertical asymptote, see how I've highlighted in yellow, should come from where the denominator equals 0. So that's at x equals 0. The VA should also come from the lowest common denominator. Okay, so two things to look at. And notice that's why there's the restriction, x cannot equal 0. All right, next up. The x-intercepts are going to be where the numerator equals 0. So these are my two factors. So my two factors would equal 0 at x equals 4 and x equals negative 2. So I have found my vertical asymptote, and I have found my x-intercept values. These are the three numbers I need to create my interval chart. So let's create that interval chart. So the first number that appears when reading left to right on the number line is negative 2. So x is less than negative 2. Then negative 2 to 0. Then 0 to 4. And x greater than 4. along the side here, remember you have to have every factor, okay, every factor of your final line. So you have to have every factor of the numerator. So don't forget this little GCF of -1. Okay, so -1 is a factor. Then you have x minus 4, x plus 2. So those are the numerators, numerator factors. And then your denominator pieces have to be there too, x. And then all those create, and I'm referring to this final answer as f of x. All right, plug in your test points. Start doing your answers. Remember, because this is just a factor of -1, that means it should be negative across the board here. Right? There's no x value to sub in, so it's just whatever its sign is. All right, then we ask ourselves, we are looking for where f of x is, so I'm just reading this right to left, so where f of x is greater than 0. Okay. So where f of x is greater than 0, so reading it this way, just because f of x is there. So that means I'm looking for where f of x is positive. Okay, and that is in this first interval and the third one. So that means my final answer is that the solution is x is element of -∞ to -2 in union with 0 to 4. Okay, or you can write in set notation here. And on a number line, that would look like this. So 0 to 4 with open circles, less than -2 as well there. Excellent. All right, let's try another one. So here we have 7 over x minus 3 is greater than or equal to 2 over x plus 3. So this time I decided to bring things to the left side. All right, so when we bring it to the left side, it's going to be 7 over x minus 3 minus 2 over x plus 3 is greater than or equal to 0. So remember, the next thing you want to do is you want to rewrite everything as one term. Okay. So I want to write this as one term. The only way I can combine two fractions with different denominators without canceling anything out, remember, is by finding an LCD. So I've got x minus 3, x plus 3, so that means the lowest common denominator is going to be their product. Okay. So remember, you are not multiplying by the LCM and canceling out. All you are doing is rewriting the first term with a denominator of this. So because it already has x minus 3, that means we have to multiply it by x plus 3. So I'm multiplying the bottom by x plus 3 here. Whatever I do to the bottom, I do to the top. Okay, so that I'm not changing its value. This term, I have to multiply the bottom by the missing factor x minus 3. Whatever I do to the bottom, I do to the top. So the -2 also gets multiplied by x minus 3. All right, so what does that leave us with? Okay. So just a nicer form, so that's 7 times x plus 3 all over the LCD, minus, notice that I'm keeping the minus on the outside here, and then putting this term in square brackets because it helps me remember that this -1 will be distributed into the terms later on. Okay, that's usually a common error. And then 2 times x minus 3 over the LCD. All right, so now let's distribute. So we get 7x plus 21 minus, and then, so this is what we're doing here, so we're just multiplying in here. Here we're doing 2 times x and 2 times -3. So we get 2x minus 6. Notice I'm maintaining those square brackets here so that you guys remember to distribute that -1 in on the next line. And notice that because they both have the LCD now, you can write it all together in the numerator all over the same denominator. Okay, now let's distribute in that -1 into both terms. All right, So we get 7x plus 21 minus 2x plus 6 all over x minus 3. X plus 3 is greater than or equal to 0. All right, so that leaves us with, when we collect our like terms, 5x plus 27 over x minus 3, x plus 3 greater than or equal to 0, where x cannot equal plus or minus 3. There are restrictions from here. All right, we cannot factor the numerator anymore, so it is fine the way it is. So now I'm just going to refer to this as f of x. And now at the side, we're just going to identify what our vertical asymptotes are and what our x-intercepts are. So remember, we find our x-intercepts wherever the numerator equals 0. Okay. So that is wherever 5x plus 27 equals 0. So let's highlight here. So x-intercepts come from the numerator. Okay. The next thing we want to do is find the VAs. Okay. Oh, sorry, that was negative 27 over 5. My apologies. So x is equal to about negative 5.4. Okay, so it's okay to convert this to a decimal number so that you can easily put it into your interval chart. So this has an x-intercept of negative 27 over 5 once you solve for x. Okay. All right, now our vertical asymptote is where the denominator is equal to 0. Okay, and we can also see that from our lowest common denominator and from our restrictions here. So that will be at plus or minus 3. So we'll highlight there. So we get our denominator equal to 0 will give us our VAs. Okay. So those are our two key features here, plus or minus 3 and negative 5.4. Those are the three numbers that will create your interval chart. So x less than negative 5.4, negative 5.4 to negative 3, negative 3 to 3, and x greater than 3. You have your 5x plus 27 and your two factors at the bottom. And once you plug everything in, you should get negative, positive, negative, positive. You go back to your question. We brought everything over to the left here, so it reads, where is the graph greater than or equal to 0? So that means where is it positive? So it's positive here and here. One thing that's interesting though about this one is that it has an equal to symbol. So remember, it can be equal to at x-intercepts. However, it cannot be equal to at vertical asymptotes because that's undefined. So you have to be careful where you put your equal to symbol. So you're going to say your solution is square bracket negative 5.4 to negative 3 circle bracket. Okay, circle bracket because that's a VA point. In union with 3 to infinity, notice again circle bracket because 3 is a VA. So with the equal to symbol, you can only put the square bracket for x-intercepts, circle brackets for VAs. Okay. Notice on the number line, that's why negative 5.4 had the closed circle, the VAs did not. All right, the steps should become very repetitive. Just to keep in mind, I also wanted you to know a common student error. When you're doing lowest common denominator, if I gave you an example like this, where both the terms, okay, so I know you'd bring one term over, right? Set one equal to 0, but I want you to notice here that the lowest common denominator for these two terms is not going to be x plus 3 times x plus 3 times x minus 3. Because these two share a factor in the bottom of x plus 3, that means your lowest common denominator is just going to be x plus 3, x minus 3. Okay, so you don't have to write it out twice, right? That's hence the word lowest. Lowest common denominator means that you want to use the least amount of terms. So that means this guy wouldn't have to change at all, because these two terms already exist in the denominator, these two expressions. However, this guy, okay, this guy here would have to be multiplied top and bottom by x minus 3, because that's just the one factor it was missing. Okay? So be careful of that. If you have a common factor in denominators, you don't have to write it out twice as the LCD. All right, so this one here, we're going to bring 2 over t plus 9 to the other side. So it becomes minus 2 over t plus 9. Our lowest common denominator, we have nothing common at the bottom, so we just have to do the product of their two factors, 4t plus 1, t plus 9. We're going to rearrange or rewrite both terms with the LCD. First, the first term's numerator and denominator will get multiplied by what's missing, which is t plus 9. Second term will get multiplied numerator and denominator by 4t plus 1, as that's what's missing. All right. So you can do everything kind of quickly in one step if you like. So notice here I immediately multiplied. So I immediately did t times t plus t times 9, right? And then I multiplied these guys in too. All right, so we get t squared plus 9t minus, notice I'm keeping, anytime a term is subtracted, I always like to kind of keep it in the brackets separate. I'll do a purple bracket here. Okay. So this part here. Minus, and then 2 times 4t plus 1 would give me 8t plus 2. Now that they both have the same denominator, we should be able to put them over the same thing. Remember here that the negative 1 gets distributed into both pieces. Okay. What happens is if you don't have those brackets, students only distribute it to the 8t and then they forget to put it to the 2. All right, so we end up with t squared plus 9t minus 8t minus 2 all over our LCD greater than 0. That gives us, when we collect like terms, t squared plus t minus 2 over our denominator greater than 0. This is a simple trinomial. Okay, that can be factored to numbers that multiply to -2 and add to 1, or 2 and -1. So that leaves us with a final expression of t plus 2, t minus 1 over 4t plus 1, t plus 9 greater than 0. I'm just going to refer to this final term as f at t. Okay, next step, find the x-intercepts. The x-intercepts are wherever the numerator is equal to 0. So again, I'll do highlighters if that helps. So x-intercepts where the numerator equals 0. So that's going to be at -2 and 1. Okay. Sorry about that. Our next step will be to highlight the denominator. That will help us find the VAs. Okay. So those will be -1 over 4 and -9. That's where the denominator equals 0. See how having it in factored form made all that so much easier. Okay. All right, let's do our interval chart. Yes, I know this is ugly. It has 4 key points. Okay, so we've got -1 over 4, -9, and then we've got -2 and 1. So that's a lot of intervals, but nothing we can't handle. Okay, so if you have 4 key points, there should be 5 intervals along the top here. Make sure you include all 4 factors in your sides here. When you complete all your work, you should get final answers of positive, negative, positive, negative, positive. So we're going to go back to our question here. Okay, our question asks for where f of t was greater than 0. So that means that's why I've highlighted these sections, because that's where it is positive. Okay. So that means the solution to this rational inequality is negative infinity to negative 9 in union with negative 2 to negative 0.25, or negative 1 over 4, in union with, and then this guy here, 1 to infinity. Okay, we didn't have the equal to symbol, so that means all those boundary values should be open circles. Okay, and our last one. Again, I brought the right term to the left side. Okay, and notice we have an equal to symbol here, so that's going to be important at the end as well. So we bring it over. We have no common factors in the denominators to make this simple, like this scenario up here that I showed. So our LCD is just going to be the product of the two, x plus 1, x minus 3. So we're multiplying the top and bottom of this expression by x minus 3. Remember, we are not changing its value or canceling it out. We are just rewriting it in a different way. The second expression will be multiplied by x plus 1 in the top and bottom. All right, that will leave us with, so again, I'm going to use our purple pen here. Okay. So it looks a little different. All right, so x plus 3 times x minus 3, we know that if we were to FOIL that, we would get x squared minus 9, okay, all over our LCD. Minus, and then I have to do x minus 2 times x plus 1. If I expand that, I'm going to get x squared minus x minus 2 all over our LCD. All right, we're going to bring those terms together. Before you do that, remember that you have to expand the negative 1 into, distribute the negative 1 into each term inside the purple brackets. Okay, once we do that, we can combine our numerators over the same denominator. What's going to happen here is the x squareds are going to cancel out, and you are going to be left with x minus 7 all over x plus 1, x minus 3. This is as simplified as it's going to get, so I'm going to call that f of x. Again, I come up with my x-intercept as wherever the numerator is equal to 0. Okay, so that is at 7. So x-intercept at 7. And then our vertical asymptote is wherever the denominator is equal to 0, and that is at negative 1 and 3. Okay, so also at the side here, let's just make sure that we also write our restrictions always at the side. So x cannot equal negative 1 and 3. Okay. And back over here, I'm also just going to write our restrictions that t cannot equal negative 1 over 4 and negative 9. Okay. Always writing restrictions with rational functions. Okay, so we've got 3 key points. That means we're going to create 4 intervals with negative 1, 3, and 7. We should only have 3 factors, so 3 rows here other than the test point. We should get negative, positive, negative, positive. And our question, because we brought it to this left side and it was greater than or equal to 0, means that we're looking for positive answers. But be careful, in our therefore statement, you can only put a square bracket with terms that are x-intercepts. Okay? So we say that the solution is x is an element of negative 1 to 3. Okay, notice circle bracket because those are vertical asymptotes, in union with square bracket 7 to infinity. And we could put the square bracket there because 7 was an x-intercept and not a VA. And that would be our final answer. All right, I hope everyone enjoyed this. Just do a lot of these, and with more practice, it'll become a bit more natural to you. Remember, you cannot cancel out denominators with rational inequalities. All right, see you next time. Good luck with the homework.